For 50 years, scientists believed a truly useful quantum computer was at least a generation away, something our grandchildren might live to see, not us. Then, in the span of 30 days, a single university quietly rewrote that timeline twice. Not once, twice. And almost nobody outside the world of physics noticed. To understand why that matters, you first have to understand just how strange and stubborn the problem of quantum computing really is. Since the 1980s, physicists have known, at least in theory, that a computer built on the rules of quantum mechanics could outperform every classical computer on Earth for certain kinds of problems. Not just a little faster, not just a marginal improvement, exponentially faster for tasks like simulating molecules, breaking modern encryption, modeling financial risk, and designing new materials atom by atom. The theory was elegant, the mathematics checked out. And for decades, that theory sat mostly on paper, because building the actual machine turned out to be one of the hardest engineering problems humanity has ever attempted. The core of that difficulty comes down to a single brutal fact about quantum bits, or qubits. Unlike the bits in your laptop, which are stable, robust, and either a 0 or a 1, qubits are almost unbearably fragile. They exist in a delicate state called superposition, holding multiple values at once, and they only stay useful for as long as they remain undisturbed. A stray vibration, a tiny fluctuation in temperature, a photon bouncing off the wrong surface, even the electromagnetic hum of nearby electronics can collapse that fragile state and destroy the information inside it. Scientists call this decoherence, and for most of the history of quantum computing, it has been the single biggest obstacle standing between an interesting laboratory experiment and a machine that could actually solve real-world problems. The traditional answer to this fragility problem was to gang up on it with sheer numbers. If a single qubit is too delicate to trust, why not spread the same piece of information across hundreds or even thousands of physical qubits, wrapping the fragile data in layers of redundancy so that even if some individual qubits fail, the overall information survives. This approach is called quantum error correction, and one of its most famous implementations is known as the surface code. It works in principle, but it comes with a catastrophic price tag. To create just one stable, reliable, logical qubit, the kind you'd actually want to use to run a calculation, engineers using the surface code often need somewhere between 1,000 and 10,000 physical qubits standing behind it, constantly checking each other for errors. Now stretch that requirement out to the scale needed for something genuinely useful, like simulating a complex molecule for drug discovery, or breaking modern encryption standards, or modeling the behavior of a new battery material at the quantum level. Suddenly, you're not talking about thousands of physical qubits, you're talking about millions. Some of the most ambitious quantum computing roadmaps in the world have penciled in target numbers well north of 1 million physical qubits just to reach the threshold of doing something practical. And building, cooling, calibrating, and controlling 1 million anything, let alone something as delicate as a qubit, is a monumental undertaking. It's the kind of number that pushes a technology from a few years away into maybe by the time your kids retire. This is the wall that the field of quantum computing has been running into for years. Physicists have proven again and again that quantum computers can work in small, controlled demonstrations. But the path from a 50-qubit chip in a laboratory to a 1 million-qubit machine capable of transforming medicine, chemistry, and cryptography has looked less like a bridge and more like a canyon. And that brings us back to Chicago. The University of Chicago, and specifically its Pritzker School of Molecular Engineering, has spent the last several years quietly becoming one of the most important quantum research hubs on the planet. It's easy to miss because the coastal tech narrative tends to focus on companies like Google, IBM, and a handful of well-funded quantum startups. But behind the scenes, a dense concentration of talent has been building in Chicago, fed by the university itself, by Argonne National Laboratory just outside the city, by Fermilab, and by a state government in Illinois that has poured billions of dollars into positioning the region as a global center for quantum technology. That infrastructure, largely invisible to the public, is exactly what allowed 2 major breakthroughs to emerge from the same place within weeks of each other. The first of those 2 breakthroughs centers on a concept with an intimidating name: quantum low-density parity-check codes, or qLDPC codes for short. Don't let the jargon scare you off, because the underlying idea is actually fairly intuitive once you break it down. Remember that the old-school surface code approach to error correction mostly relies on qubits, checking their immediate neighbors, the way you might ask the person sitting right next to you to double-check your math. It's simple, and it's reliable, but it's incredibly inefficient because it requires an enormous number of neighbors clustered together to catch every possible mistake. A team led by Professor Liang Jiang at the University of Chicago, working alongside researchers from Harvard, Caltech, the University of Arizona, and the quantum computing company Quira, asked a different question. What if, instead of only checking with your immediate neighbor, A qubit could reach across the entire system and compare notes with qubits far away, ones it wouldn't normally be able to talk to at all. That's the essence of a qLDPC code. It uses a smarter, more mathematically efficient error detection structure that draws on relationships between distant qubits, not just adjacent ones, allowing the same level of error protection to be achieved with dramatically fewer physical qubits. The theory behind qLDPC codes had actually been around for a while, floating through academic papers as a promising but largely impractical idea. The problem was hardware. On most existing quantum computing platforms, qubits are physically wired or trapped in fixed positions, which makes it nearly impossible for a qubit sitting on one side of a chip to directly interact with a qubit sitting on the other side. It's a bit like knowing in theory that a phone call across the country would be incredibly useful, but not having any telephone lines to make it happen. The mathematics of qLDPC codes existed. The hardware to actually implement them did not. That's where the second half of this breakthrough comes in, a hardware innovation called reconfigurable atom arrays. Instead of using qubits that are permanently fixed in place, this approach uses individual neutral atoms that are trapped and then physically moved around using finely tuned laser light, almost like invisible robotic arms, picking atoms up and repositioning them mid-computation. With today's reconfigurable atom array systems, researchers can control and manipulate more than 1,000 physical qubits with remarkably high fidelity, and critically, they can connect qubits that are separated by relatively large distances within the array. Suddenly, that long-distance phone call becomes possible. A qubit on one side of the system really can compare notes with a qubit on the other side because the laser-guided atoms can be shuffled into whatever configuration the error correction code actually needs at any given moment. When the University of Chicago team combined the mathematical elegance of qLDPC codes with the physical flexibility of reconfigurable atom arrays, the result was a genuine breakthrough. Their blueprint demonstrated a system that could achieve a better error rate than the traditional surface code while using only a few hundred physical qubits, instead of the thousands typically required. According to the researchers, this new approach could reduce the number of physical qubits needed for practical, fault-tolerant quantum computing by a factor of 10 to 20. Translate that into real numbers, and you're looking at bringing the total qubit requirement for a genuinely useful quantum computer down from the millions into the tens of thousands. That's not a minor improvement. That's the difference between a project that might get funded in this decade and one that keeps getting pushed into the indefinite future. It's worth pausing here to appreciate what that kind of reduction actually means in practice, because the significance can get lost in the numbers. Every physical qubit in a quantum computer needs to be controlled, cooled to temperatures colder than deep space, calibrated individually, and continuously monitored for errors. The engineering complexity of a system doesn't scale gently as you add more qubits. It scales brutally, with cabling, cooling infrastructure, and control, electronics multiplying in complexity as the numbers grow. Cutting the qubit requirement by a factor of 10 or 20 doesn't just save money. It fundamentally changes what's physically buildable with today's engineering capabilities, and it moves certain fault-tolerant quantum computing architectures from theoretical possibility into something that starts to look like an actual near-term construction project. Naturally, a discovery like this made waves when it resurfaced prominently in the science and technology press, with commentators calling it the shortcut the field had been waiting decades to find. And that framing isn't unreasonable. Quantum low-density parity-check codes combined with movable atom arrays represent one of the most credible, hardware-grounded proposals for solving the qubit overhead problem the field has produced in years. It is, quite literally, a blueprint showing how a much smaller number of physical qubits could achieve the same fault tolerance that used to require armies of them. But here's where the story takes an even more interesting turn, because the University of Chicago team didn't stop there. Just weeks after this qLDPC and atom array framework captured renewed attention, the same broader research effort pushed the idea even further, producing what amounts to a second related shortcut. This follow-up work focused on something researchers call ultra-high-rate quantum error correction, and it's worth understanding why the word rate matters so much in this context. In the world of error-correcting codes, whether we're talking about quantum computers or something as mundane as a hard drive storing your family photos, the term encoding rate describes the ratio between how much useful information you're protecting and how many total resources you need to protect it. A low encoding rate means you're burning a huge number of physical components just to safeguard a small amount of actual usable information. A high encoding rate means you're squeezing far more protected information out of the same physical resources. In classical computing, engineers have long been able to design error-correcting codes with encoding rates comfortably above 50%, meaning more than half of your physical resources are doing useful, information-carrying work, rather than just serving as backup and redundancy. Quantum error correction, though, has historically struggled to get anywhere near that kind of efficiency. the peculiar mathematical constraints of quantum mechanics, things like the no-cloning theorem, which states that you fundamentally cannot make a perfect copy of an unknown quantum state, make it far harder to design codes with high encoding rates. For years, most practical, hardware-feasible quantum error-correcting codes operated at encoding rates well below what classical engineers would consider efficient, which is exactly why so many physical qubits were needed to protect just a handful of usable logical qubits in the first place. The follow-up research out of the University of Chicago tackled this efficiency problem head-on. Building on the same foundation of reconfigurable neutral atom arrays, researchers developed a new family of qLDPC codes, specifically engineered to push encoding rates higher than what earlier constructions had achieved, moving into a regime where more than half of the quantum resources involved are doing genuinely useful, information-preserving work. A benchmark that has long been common in classical computing, but has remained stubbornly difficult to reach in the quantum world. The work builds on a hardware-aware design philosophy, meaning the codes weren't developed in a mathematical vacuum and then handed off to engineers to figure out later. Instead, the codes were constructed with the actual physical capabilities and limitations of atom array hardware, baked in from the very beginning, ensuring that the theoretical efficiency gains could realistically translate into something buildable in a laboratory, not just something elegant on a whiteboard. This is precisely why the framing of a second shortcut in 1 month resonated with people paying close attention to the field. It wasn't simply that the University of Chicago produced one clever paper and then, coincidentally, produced an unrelated clever paper shortly after. It was that the same underlying architecture, reconfigurable atom arrays paired with increasingly sophisticated qLDPC codes, kept yielding new efficiency gains in rapid succession, each one chipping away further at the qubit overhead problem that had defined the field for years. First came the demonstration that qLDPC codes on movable atom arrays could slash qubit requirements by a factor of 10 to 20. Then, in short order, came a refinement showing that the encoding rate of those same codes could be pushed significantly higher, meaning even more of the hardware researchers do eventually build would be doing useful computational work rather than simply propping up redundancy. It's tempting, hearing about back-to-back breakthroughs like this, to assume they came out of nowhere, as if two lucky lightning strikes hit the same building. But that's not how scientific progress works, and it's not how this particular story unfolded. What actually happened is the natural product of sustained compounding investment in a single research direction. Professor Zhang's group didn't stumble onto qLDPC codes on reconfigurable atom arrays by accident. This is an idea they and their collaborators have been developing or refining and stress testing for years, going back to earlier theoretical work on constant overhead fault-tolerant quantum computation using exactly this kind of architecture. Each new paper builds on the mathematical scaffolding of the last one, tightening the bolts, closing gaps, and squeezing out additional efficiency. 2 announcements in 1 month doesn't mean 2 isolated strokes of luck. It means a research program has reached a point of momentum where incremental improvements are arriving faster than the outside world can fully absorb them. That kind of momentum doesn't exist in isolation either. It's worth zooming out for a moment to appreciate just how much quantum activity has been converging on Chicago in recent years, because the qLDPC and atom array story doesn't exist as an isolated event. It's one especially prominent thread in a much larger tapestry. Around the same broader period, researchers at the University of Chicago's Pritzker School of Molecular Engineering, led by assistant professor Tian Zhang, published work showing they had dramatically extended the coherence times of individual erbium atoms used in quantum communication systems, pushing coherence from roughly 1/10 of a millisecond up to more than 10 milliseconds, with some demonstrations reaching 24 milliseconds. That improvement in coherence time translates directly into distance, theoretically enabling quantum computers to stay entangled and communicate with each other across distances nearly 200 times greater than what was previously possible. Distances that start to make a genuine city-spanning and eventually continent-spanning quantum internet look like a realistic, long-term engineering goal rather than pure science fiction. Elsewhere on the same campus, researchers turned a protein found inside living cells into a functioning quantum bit, blurring the line between biology and quantum technology in a way that earned recognition as one of the field's top breakthroughs of the year. Other teams at the university have been experimenting with using sound rather than light to carry quantum information between components, exploring whether tiny mechanical vibrations called phonons might offer more deterministic, less randomness-prone behavior than the photon-based systems most quantum architectures currently rely on. And in a broader collaborative report published alongside researchers from Stanford, MIT, the University of Innsbruck, and Delft University of Technology, scientists explicitly compared the current moment in quantum technology to the earliest days of the transistor, arguing that the foundational physics has now been established and functional systems genuinely exist, and that what remains is less about proving the science works and more about the difficult, unglamorous work of engineering, partnership building, and scaling. Taken together, all of this paints a picture of a research ecosystem that has quietly reached a kind of critical mass. The University of Chicago isn't producing occasional, isolated quantum headlines. It's operating something closer to a continuous pipeline of incremental, compounding advances, spanning error correction, quantum networking, biological qubits, and fundamental materials science, all feeding into the same overarching goal of making quantum computing genuinely practical rather than merely theoretically possible. When you understand that context, the idea of two related breakthroughs emerging within the same month stops looking like an anomaly and starts looking like exactly what you'd expect from a research program operating at this level of intensity and coordination. There's a geopolitical dimension here that rarely makes it into the popular conversation, but it helps explain why so much money and talent keeps flowing toward places like Chicago. Quantum computing isn't just a scientific curiosity anymore. It's widely regarded as a strategic technology, on par with advanced semiconductors, capable of shaping economic and national security advantages for decades to come. Governments, from the United States to China to the European Union, have poured billions into quantum research, racing to avoid being left behind on a technology that could eventually undermine existing encryption or unlock breakthroughs in materials and pharmaceuticals ahead of their rivals. Illinois has made quantum technology a centerpiece of its economic strategy, funding new research campuses, specifically to keep talent and investment anchored in the region. That kind of sustained backing is part of why a single university lab can produce two significant advances within 1 month rather than one every few years. So what does any of this actually mean for the rest of us? People who will never personally build or operate a quantum computer, but who might still feel the ripple effects of what happens inside these laboratories. The honest answer is that meaningful, tangible impact is still likely years away, and it would be irresponsible to suggest otherwise. These breakthroughs are, by the researchers' own careful language, blueprints and frameworks. They represent enormous theoretical and architectural progress, but they have not yet been fully realized as a complete, working, million times more capable quantum computer sitting in a data center somewhere. The gap between a compelling scientific blueprint and a deployed, commercially useful piece of technology can still take years, sometimes even a decade or more, to close, and plenty of promising quantum computing proposals throughout history have run into unexpected engineering obstacles once teams actually attempted to build them at scale. That said, dismissing this kind of progress as merely academic would be its own mistake. Reducing the physical qubit requirement for fault-tolerant quantum computing by a factor of 10 or 20 is exactly the kind of foundational shift that tends to precede periods of rapid, almost sudden-seeming technological acceleration. Think about how transistor miniaturization quietly compounded for years before anyone outside a small community of engineers noticed that computing was about to transform every industry on the planet. Efficiency gains, like the ones coming out of Chicago, don't usually make for flashy, easily digestible headlines because there's no dramatic demonstration, no computer visibly outperforming a supercomputer in a live test. Instead, they work by lowering the practical bar for what counts as buildable, one careful, mathematically rigorous paper at a time, until suddenly what looked impossible a few years earlier looks merely difficult, and then eventually looks routine. Consider the fields that stand to be reshaped once fault-tolerant quantum computers do become practical at scale. In medicine, quantum computers could simulate the behavior of complex molecules with a level of precision classical computers simply cannot achieve, potentially accelerating the discovery of new drugs and therapies by years, because instead of relying on trial and error laboratory experimentation, researchers could model how a candidate molecule interacts with a target protein at the quantum level before ever synthesizing it physically. In materials science, the same kind of quantum simulation could help engineers design better batteries, more efficient solar cells, and entirely new categories of materials with properties that don't exist in nature yet, because the underlying quantum interactions between atoms could finally be modeled accurately rather than approximated. In cybersecurity, the picture is more double-edged. Sufficiently powerful quantum computers could theoretically break many of the encryption standards that currently protect financial transactions, private communications, and government secrets, which is exactly why so much parallel research effort is currently going into developing quantum-resistant encryption methods designed to stay secure even after large-scale quantum computers eventually arrive. It's also worth acknowledging a healthy dose of scientific skepticism here, because responsible reporting on any emerging technology means resisting the temptation to declare victory prematurely. The qLDPC and atom array framework remains, in the researchers' own words, still largely theoretical, even as scientists are rapidly developing the atom array hardware platforms that move toward practically implementing error-corrected quantum computation. There is a meaningful difference between a mathematically sound blueprint that reduces theoretical qubit overhead and a physically constructed machine that reliably runs useful calculations day after day, immune to the countless small imperfections that always emerge when moving from elegant theory into messy laboratory reality. Every additional atom that needs to be trapped, moved, and precisely controlled introduces new opportunities for error, new engineering headaches, and new unexpected physics that doesn't always show up cleanly in a mathematical model. And yet, that healthy skepticism doesn't erase the genuine significance of what's happening here. Skepticism about timelines isn't the same as skepticism about substance, and the substance behind this story is unusually strong. This work has been published in serious, peer-reviewed venues, including Nature Physics, and it involves collaboration across some of the most credible institutions and companies in the entire field, from Harvard and Caltech to Quera, a company built specifically around commercializing neutral atom quantum computing hardware. This isn't a story about a single lab making an unverified claim that fails to hold up under scrutiny. It's a story about one of the most rigorous, well-resourced quantum research communities in the world, producing consistent, incremental, mutually reinforcing progress on one of the field's hardest problems, at a pace fast enough that two significant advances landed within the same month. There's also something worth saying about why stories like this so easily slip past public attention, even when their long-term implications are enormous. Quantum computing suffers from a peculiar communication problem. The underlying concepts are genuinely difficult to explain without either oversimplifying to the point of inaccuracy or drowning the audience in dense technical jargon that causes most people to simply tune out. Terms like qLDPC codes, reconfigurable atom arrays, and fault-tolerant thresholds don't lend themselves to viral soundbites the way a flashy new smartphone or a dramatic AI demonstration does. But the pattern we've seen out of Chicago, and frankly out of the broader quantum computing field over the past couple of years, deserves more public attention than it typically receives, precisely because the technology being quietly assembled behind these dense academic papers has the potential to reshape medicine, materials science, cybersecurity, and computing itself in ways that will eventually become impossible to ignore. So where does this leave us, looking forward from this exact moment? The University of Chicago's back-to-back contributions to the qLDPC and reconfigurable atom array approach represent a meaningful tightening of the gap between quantum computing's grand theoretical promise and its practical buildable reality. The qubit overhead problem, which has haunted this field since its earliest days, is not solved, and it would be dishonest to claim otherwise. But it is measurably, verifiably smaller than it was even a few years ago, and it continues shrinking at a pace that has caught the attention of researchers across the world, not just casual observers. Every factor of 10 reduction in required qubits, every incremental increase in encoding rate, every extension of coherence time brings the timeline for a genuinely transformative quantum computer closer, even if none of these individual steps feels dramatic enough on its own to dominate a news cycle. 50 years ago, the idea of a truly useful quantum computer belonged almost entirely to theoretical physicists scribbling equations that most of their contemporaries assumed would never leave the chalkboard. Today, inside laboratories on Chicago's South Side and in similarly ambitious labs scattered across the world, that theory is being methodically, patiently, and increasingly rapidly converted into hardware, one carefully engineered blueprint at a time. 2 shortcuts in a single month might not sound like the kind of headline that changes the world overnight. But history has a consistent habit of remembering exactly these kinds of quiet, compounding moments as the true beginning of something much larger, long after the world eventually catches up to what a small group of researchers already understood.